In this video, we're going to work example problems involving comparison tests. Comparison tests to determine whether or not a series is convergent or divergent. And so remember, there's the standard comparison test, and then there's also the limit comparison test. And for any of these problems, we could use either one of those. And the general idea is that you don't have to do it this way, but the general idea is that you start with you're doing a general comparison test, and then if you end up finding that you didn't get the convergence or divergence relationship that worked for the comparison test, it was one of the results that are inconclusive, right? Like a smaller series converging compared to a larger series. Then from there, you can go to the limit comparison test with those two series to try and get the answer. Now, you don't have to do it that way. You can use the limit comparison test from the start and with any two series. It doesn't matter, but that's the general way we're going to approach these problems. We're going to start by doing the general comparison test. If we get the answer from that, then we're done. But if we end up getting one of those inconclusive conclusions of the general comparison test, then we'll go to the limit comparison test. Okay, now, before we get started, one more thing to note is that it's not like for each one of these problems we couldn't use the integral test. Okay, a lot of these problems we could find out if it's convergent or divergent using the integral test. But these are just we want to practice the comparison test. We want to get used to how all of these different tests work, so that given a general series, we can figure out if it's convergent or divergent, if one or more of the different tests won't work, and maybe only one of the methods we know will work. Okay, so let's get started. Looking at this series here, what we notice is that, so for all n, these sequence terms are always greater than 1 over n cubed. And the main reason I want to use this as our b sub n, here's a sub n, and here's b sub n, is because, well, one, you can see that just by removing the 8 here, we get a relation to where, like, the new sequence we've created is always less than or equal to, or less than, or it's either always greater than or always less than our main sequence. That's one reason I did that. But another reason was that we know what this is. We know the behavior of this, the convergence behavior of a series with this a sub n in it. This is a p series with p is equal to 3. We know this is convergent. Okay, so that's great. So does that mean we've solved the problem? Well, no, it just depends on if there's 4 possibilities of the comparison test, and only 2 of them give you the result, a conclusive result. So, okay, these terms are always from n is, I guess, from starting at 1, this is the case, even starting at 1, going from 1 to infinity, but it doesn't have to start at 1, but these terms are always less than these terms. And we know that this is convergent. Or no, I'm sorry, I got this wrong. This is greater than. Because you add 8 and you get a bigger denominator. So this, okay, yeah. So these terms are always greater than these terms, but we know this series is convergent. So it's like this. It's like we have a series that's always greater than another series, but we know the series that's greater than the other series is convergent. So that means this is going to be convergent. Okay, just looking at this, the first thing I notice is that if we took this 1 off, we would have something that's always less than our given sequence. So, okay. There's the sequence, and if we took that 1 off, we would have this. But these cancel, so you got 1 over root n. 1 over n to the 1/2, right? Okay. Well, the first question is, are we familiar with this kind of a series with this a sub n? Yeah, this is a p series with p less than 1, so this is divergent. All right, that's good. But what does this still, is this conclusive though with the inequality? Well, okay, this is always, this series here with this sequence put into a series going from 1 to infinity is always less than this, and we know this is divergent, so that does work, right? We've got a series that's always less than another series. We know this series is divergent, so the one that's greater than it's definitely going to be divergent. Okay, looking at this, what I see is if we took off this 3 here, we would end up with a geometric series. So, okay, like if we take off the 3, what do we have? 9 to the n over 10 to the n. That's 9 over 10 to the n, right? That's a geometric series and a convergent one because the common ratio is less than 1. Okay, now how does this relate to the original a sub n? Well, this is always less than this because we always have a bigger denominator. Okay, this is convergent, and this is always greater than this, so that means this is convergent. All right, if we take off the natural log, that's what I noticed about that is we know about this series behavior. We know this is the harmonic series, and this is divergent. Okay, that's one aspect of what I like about using this as a comparison. And then, so how does this relate to natural log of k over k? Well, this is always going to be greater than, at least starting at like 3. From 1 to 2, it's not, but it doesn't. It's all about just you have a start point and then going to infinity. This is the case. All right, so that's great. We have a comparison with where one function or one a sub n is greater than another or less than another, all the way to infinity, and we know about the convergence behavior of one of those a sub n's. That's great. But then, is it one of does this result in a conclusive answer to the convergence question? If it doesn't, we'll have to find another function. We'll have to find another comparison. Okay, well, this is divergent, and this is always less than this, so that means this is divergent. Okay, so here, I just want to try anything. This looks like a mess. So if we took off this 4k plus 3 here, we would get what? We've got k to the 1/3 over k, the square root of k cubed, which is, okay, so 1/3 minus 3/2 is, so, okay, we've got 1 over k to the 7/6. Okay, so, all right, let's bring that here. Now, how does that relate to this? Okay, well, we took this term out of the denominator. So this is always going to be greater than this. Okay? Now, what about what is this? This is a p series with p is greater than 1. So this is convergent. Okay? This is always greater than this. So that means this is convergent. Right? The main idea was that we're converting this to like a p series or a geometric series. So you can look at a lot of a sub n's and convert it to that and also have the constraint that one is always like greater than or less than the other. Okay, so here, if we take off the cosine of n, we've got this, which is, this is a geometric series. 1 over e is less than 1. This is a convergent, the sequence that corresponds to a convergent geometric series. Okay, now if we write, how does this compare here? And so, okay, cosine of n is going to oscillate between 1 and minus 1. It's not going to technically do that because we're going by the integers, but you can think of it that way, right? You have to only at, it would be for like pi, 2 pi, 3 pi, 4 pi, but those are never integers. That's where it's going to 1 and minus 1 and 1 to minus 1. But still, we can think about it, just think about it in general, that cosine of n oscillates between 1 and minus 1. So here, this is oscillating between the numerator, between 0 and 2, which we can't write an inequality here. But remember, you're really flexible when it comes to setting up a comparison. Don't feel like you're constrained, like, oh, well, like you don't know where to go. You can make, this is any function you want. This has nothing to do with the fact that we took off the cosine of n, like now we can't change this. Not at all. We can put whatever we want here. So let's do this. Let's say, just put a 3. Why not? So now this is true, right? This is going to oscillate between 0 and 2, and this will always be 3, and the denominators are the same. Okay, and so the only issue is with putting that 3 is that, do we still have a series that we understand? And yeah, we do. So we can write it this way. So and we know this is convergent, and that just whatever it converges to, multiply by 3. So okay, so this is convergent. This is always greater than this, so this is convergent. Okay, so I look and I see, let's take off that 2 and see what happens. So this is, we get 4 times 4 over 3 to the n, right? You see, we can separate this into 4 to the n times 4 to the 1. So you have 4 to the n over 3 to the n. And we know that this series is going to be divergent. It's a geometric series with the absolute value of r greater than 1. Okay, so how does that compare to this? Well, okay, we're always subtracting a 2 from the denominator. So the denominator here is always smaller, so this is greater. This is always greater than this, and this is divergent, so this works. Okay, I mean, I just see that this 1 here, so 1 over, take off the 1, the square root of n squared is just n. We know that's divergent. Okay, we always have a bigger denominator here, so this is less. Okay, so this is always greater, and this is always less. This is divergent. So this is inconclusive, this test, right? We've got a function we know that's divergent and a function that's always less than that function. So this could still be potentially convergent or divergent, okay? So what we're going to do is go to the limit comparison test. And again, as I mentioned at the beginning of the video, you don't have to do every analysis, series analysis this way, like starting with the comparison test, the standard comparison test. And, you know, if you get an inconclusive answer, go to the limit comparison test. You could start with the limit comparison test, but that's just how we're doing it for these problems. So, okay. In general, we might have some problems where we actually start with the limit comparison test. If we might have a problem where we look and we see that we can't really do a simple simplification to get a clean comparison sequence like this. And then in that case, we'll just go straight to the limit comparison test. But all right, if we, so the limit comparison test is you're taking the limit as n approaches infinity of this divided by this or this divided by this. So let's do this divided by this. And so what we get there is, okay, now if we take, so n divided by square root of okay, so now let's take the limit as n approaches infinity. Okay, so this limit is equal to 1, which is greater than 0. This limit here needs to converge and also converge to something that's greater than 0. And that, okay, so what does that mean, though? What does that tell us? That tells us that both of these sequences, they either both converge or both diverge. Well, we know that this diverges, so therefore this is divergent. Okay, here, now what if we removed both of these n's? We get 1 over n cubed, which we know is convergent. Okay. Now, how do these two compare? Well, all right. If you have, so if we have 50 over 100, how does that compare to 55 over 105? Right? We just added 5 to the numerator and denominator. So 55 divided by 105 is bigger than 0.5. Right? What if we had 152 divided by 357, and then we added 10 to the numerator and denominator? 162 divided by 367. It's bigger. Okay, so this is bigger than this. Okay, this is convergent, so this test is inconclusive. Okay, so now we would normally go ahead and divide these two, but let's go with the method that they talked about in the textbook. So with something like this, with a ratio like this, we can make the b sub n be the order of the highest order term in the numerator divided by the highest order term in the denominator. But then that's fine, but we have to make sure that this is actually a sequence we understand, and it is. Is that what we had before? No, we had 1 over n cubed. So we'll do 1 over n squared. We know 1 over n squared is convergent. So, okay. Let's do, we'll do a sub n divided by b sub n. So we've got n squared times n plus 1 over then n squared plus 1. So this is the limit as n approaches infinity of n times n plus 1, which that's going to go to infinity. So let's do b sub n divided by a sub n. So you've got n cubed plus n over n squared times n plus 1. So n squared plus 1 over n squared times n plus 1. So you've got n, this is n squared plus n. Okay, now if we divide the numerator in denominator by n squared, you get as n goes to infinity, this goes to 1, which is greater than 0. So, okay, this converges. That means this converges. Okay, so looking at this, I can't see a way to make a simple adjustment to where we have like a p series or a geometric series comparison sequence. So let's do, we want to create a ratio, a b sub n. You know, the general idea we're going to do the limit comparison test. So we want to, with a ratio like this, a general way you could look at it is do the highest order term in the numerator divide by the highest order term in the denominator. And that's going to be your b sub n. So 1/2 divided by into the 1/2 divided by into the 1 is, okay, and so now we have to check, is this something we understand? And this is a divergent p series. Okay, so now the limit as n approaches infinity, and what did we do in the previous problem? We did b sub n divided by a sub n. Let's do that. So what you end up with is 2 plus n over square root of n like that. So you've got, okay, so let's put this into the calculator because I don't want to get into this kind of limit here. So, okay, n plus 2 this is equal to 1. So this limit, which is greater than 0, so that means that we can say that a sub n and b sub n both either both converge or both diverge. Well, we know b sub n diverges, so that means this is divergent. Okay, so here I don't see a simple way to convert this into something we can just use for the general comparison test. So let's go with just, okay, we're going to say b sub n is equal to the order of the numerator, and then the order of the denominator is n to the 4th, right? So, okay, let's do b sub n divided by a sub n. Here's a sub n. So we've got 2n okay, so you've got okay, and so here we want to expand this out. So we've got 2 and then 1 plus 2n squared plus n to the 4th. And then here we've got 5n cubed plus 2n to the 4th. Okay, so 2 plus okay, so now let's divide the numerator and denominator by n to the 4th. So as n approaches infinity, this approaches 2 over 2, which is equal to 1, greater than 0. So, okay. Now, we should have, I kind of I skipped a step here. We need to check that we understood this b sub n. I could have wasted all this effort because this is worthless if we don't know what b sub n does. And so even with this 2 up here, we still can bring out the 2. This is a convergent p series. So that means that this is convergent. Okay. So we can take off both of the 1s, and then we saw in the previous problem what that means. So yeah, let's do that. Let's take off both of the 1s. What do we have? We've got, so e to the n over n e to the n, which is 1 over n times e over e to the n, 1 over e, but 1 to the n is just 1, so this is 1 over n, and we know that's divergent. This is the harmonic series. So, okay. Now, how does this relate? Well, we saw this is going to be greater than. So this is divergent, and it's always less than this. So that means this is divergent. Okay. So I don't see. Okay, if we took off this 1 here, what would happen? We'd have 1 over n squared over e to the n, which is, so 1 over e to the n squared e to the n. And in that case, this is always, okay, so in that case, this is always bigger than this because these two are the exact same, except we're just not adding this 1 to the square. So this will always be bigger. But, okay, there's nothing we could do with this, though, as far as is it convergent or divergent. But if we took out the e to the n power, what would that do? That would make this bigger, which would mess this up. Right, because if we took out the e to the n and it only made this smaller, then we'd have 1 over n squared. But if we take out the e to the n, we don't know what that means if now this becomes bigger and overtakes this. It probably would. Well, okay, if what I notice is that if we could get rid of this e to the n, then we'd have this, as n goes to infinity, converges to something greater than 0. So let's see if we, all right, let's come back to the start here. So we could get rid of that e to the minus n by dividing another sequence that has e to the minus n in it. So let's do this. Let's say that b sub n is 1 over e to the n. That's e to the minus n. And so that's great because when we take the limit as n approaches infinity we'll do a sub n divided by b sub n. That's going to go to 1. Okay, great. But the only caveat is, we have to know what this does, converges or diverges. Well, this is a geometric sequence where the r is less than 1. So this converges. So you can see if we'll do a sub n divided by b sub n. B sub n is e to the minus n. You could do a sub n divided by b sub n or b sub n divided by a sub n. It doesn't matter. And we're left with this. As n approaches infinity, this goes to 0, 1 squared. So this converges. Okay. So to me, what I think about is that you can divide expressions with factorials and end up getting rid of the factorial. So let's go straight to the limit comparison test. And what we're going to do is, so like, okay, if let's say we had 1 over n plus 1 factorial, okay? Let's say this was going to be our b sub n. if we divided a sub n by b sub n, or vice versa, let's divide a sub n by b sub n. What we get is n plus 1 factorial over n factorial. So what do we do with this? Well, we say this, right? That's the same. This is n plus 1 factorial. So this simplifies to n plus 1. Okay, so with that in mind, let's choose a b sub n, because we need to choose something that results in a sequence that we know converges. Well, okay, actually, the more I think about this, okay, we can actually say that we can actually do just a comparison, straight up comparison test. If we said, so 1 over 2 to the n. Okay, I believe factorials are known for rising way faster than like exponentials. So, okay, 2 to the 10, and then 10 yeah, exactly. Right. So we can say that this will always be less than this. Okay, but this is a geometric series that converges. Or no. Wait, it's the other way. This is always greater because the 2 to the n is always smaller than n factorial. Okay, so this converges. This is always greater than this, so this is convergent. Okay, this one, what we're going to do is we're going to say that the b sub n is 1 over n. We know that this diverges, right? So why are we doing this? Because this is one of those special limits that they had to use like a geometric argument to evaluate it. So, okay, we divided a sub n by b sub n, but if we let theta equal 1 over n, and this is the limit as theta approaches, all right, so as n approaches infinity, theta approaches 0, right? So we've got sine of theta over theta, which is equal to 1. That's greater than 0. We know this is divergent, so that means this is divergent.